The objective of this video is to introduce the equivalent circuit model for continuous conduction mode and discontinuous conduction mode operation of a power converter. We are changing our mindset from design, where we solve an inverse problem, to control, where we need more knowledge of the converter behavior. We are now interested in sensitivity between control variables and converter output, and the various circuit operating behaviors. We need to understand not only the circuit behavior, we must also be able to express it quantitatively. The electrical engineer's tool of choice is an equivalent circuit. That is our bread and butter analysis tool. As you may have studied in previous coursework, we can take an induction motor, which is a very complicated device with speed dependency and coupled magnetic fields. We can take this complicated device and we can draw an equivalent circuit for it. We solve this equivalent circuit to determine its quantitative operating behavior based on the voltage applied. The equivalent circuit is something we know and understand well. Also, in previous courses, you have learned about the transistor. This is another very complicated device with semiconductor physics that govern its p-n junction operation, its depletion region, built-up charge, and so on. All of this is based on design decisions such as the semiconductor doping, as well as control decisions such as the current or voltage applied. We can take this complicated device and draw an equivalent circuit with a current gain of beta and a dependent current source. And this equivalent circuit allows us to take this rather complicated system and model only the salient behavior, only the details that we need for our operation within a broader system. So just like all of this, we now want to take our power converter and express it as an equivalent circuit. We want something that is easy to solve. We don't need to look at all the waveforms all of the time. We want to be able to change the DC voltage so much, or the duty ratio so much, and see what the inductor current becomes, what the capacitor voltage is going to do. This will be useful for two things. First, it will be useful for predicting performance, and second, it will be useful for designing closed-loop regulators. Specifically, I'm talking about deriving transfer functions. This is something that we will be discussing in later videos. This video is setting the stage for future analysis. So our power converter consists of several devices. It has transformers, inductors, transistors, diodes, capacitors, resistors. We have circuit components or circuit models for most of these devices already. But what is the equivalent circuit for a switch? It's either a short circuit or an open circuit. We want to remove this time dependency. We want to be able to talk about the converter behavior in a steady state sense, which is at a lower speed than the switching frequency. So we don't want to have this binary on-off sense for deriving our equivalent circuit because that makes it difficult to analyze transfer functions, or to develop transfer functions, or to analyze a circuit state in a steady state mode. So we'll start by drawing our single pole double throw switch. And as we've talked about several times, how we realize this with semiconductors depends on the direction of our pole current and our throw voltage. If everything is as I've labeled it right now, we might use the active-passive realization that we talked about for the buck converter. Or we could use a fully active realization where we use a switch, an actively controlled switch in both the top and bottom throws. I should note that this fully active realization is also what we do when we have AC current flow. So when I'm saying active and passive, what do I mean? Well, an active device, we'll use the letter A, is a device that we actively are able to control whether it's on or whether it's off. So we're talking about a MOSFET or a BJT or a IGBT. A passive device is something that the circuit conditions govern whether or not it's turned on. So that's a diode. If we apply a forward voltage across the diode turns on. If we apply a reverse voltage across the diode turns off. So with the active device, we get to specify the duty ratio that it's on. With a passive device, our circuit conditions determine the duty ratio. And so far we haven't made this type of distinction because in the videos so far, we've considered that our current source, our pole current, is sufficiently stiff so that we always just assume that our diode will be on whenever our MOSFET is off. So that's to say that we've assumed that our top throw duty ratio is equal to dA, where dA is the active duty ratio, or the duty ratio of the active device, and that our bottom throw duty ratio is equal to 1 minus dA. And this was under the conditions of continuous conduction mode, or CCM. Okay, so CCM and DCM. What's the difference? Well, CCM refers to continuous conduction mode, and it is the typical DC-DC converter operation that we have so far considered. It represents the case where the current through the inductor is never zero for any interval. While discontinuous conduction mode represents the case where our pole current ripple, or our inductor current ripple, has become so large that the current through the inductor or through the pole becomes zero for an interval of time. And the point of this is that when our active switch is off and our inductor current decays to zero, if we have a passive device for the second throw, the passive device will stop conducting once the inductor current becomes zero. So this means that, well, we can control the active duty ratio, that is the duty ratio of our top device up here. Our bottom device becomes something else. The duty ratio becomes something else. We're just going to call it complicated right now for DCM. And in this video today, we are not going to define what this complicated duty ratio is. That will be our next video. But we're going to consider this case. We're going to talk about what it means and why it happens. Now, I want to distinguish here the active-passive realization from the fully active realization. In the fully active realization, again, our top switch's duty ratio is dA. And in this case, since we're able to actively control the bottom switch, it will also have a duty ratio of 1 minus dA, regardless of whether it's in continuous conduction mode or discontinuous conduction mode. And actually, the right way to say this is that it doesn't enter discontinuous conduction mode. By being able to actively control that switch, we prevent the case where the inductor or pole current goes to zero for an interval of time. And so if you were to ask me to design a buck converter for you, I'm going to do the fully active realization. Anytime, any day. But I'm a professor. I'm not at a company trying to make a low-cost product. The reason that you choose the active-passive realization is because you're saving on component cost. You have to only buy one MOSFET instead of two MOSFETs. You only need one MOSFET gate driver instead of two MOSFET gate drivers. Okay, so we've introduced this concept of continuous conduction mode and discontinuous conduction mode and active and passive devices. Now let's get on with the equivalent circuit. So we take our single pole double throw converter, and the equivalent circuit for this is as follows. So at first pass, this should not be a surprise. We've drawn two rectangular shaped sources. These are dependent sources. This means that our pole voltage is going to be equal to a duty ratio times our throw voltage. And we've called this duty ratio DE, or equivalent duty ratio. And we're seeing that our top throw current is going to be equal to a duty ratio times our pole current. And again, we're using the equivalent duty ratio DE. So we've assumed that this is true in our previous analysis of the DC-DC converters, of the single pole double throw switch. We've always analyzed our pole voltage as being a duty ratio times our throw voltage, and we've always analyzed our top throw current as being the duty ratio times our pole current. But we're going to formalize this now. And let's start by making the following observation, that this situation preserves power balance. If it didn't preserve power balance, it would not be a good equivalent circuit. And we can check that pretty easily. The power into the throw, in across the throw, is equal to our throw voltage times our top throw current. And then the power delivered to the pole is equal to our pole voltage times our pole current. And excuse me, we're going to replace these lowercase IPs with capital IPs to indicate that we're talking about average quantities now. These are not instantaneous quantities. So clearly these two expressions are equivalent, and we're satisfying the first law of thermodynamics. We're conserving energy, or we're conserving power. Okay, so now let's talk about the strange quantity dE. dE is equal to dA, or the duty ratio of our active device, in continuous conduction mode. And it's a more complicated situation in discontinuous conduction mode. Great, so now let's apply this to analyze a converter that's operating in continuous conduction mode. Clearly this is a buck converter, and we've got a duty ratio assigned to the MOSFET. This is the active duty ratio, and a duty ratio assigned to the diode, which is the passive duty ratio. So I want you now, in your notes, to draw another circuit below this, which is the same circuit but replaces the switching devices with the equivalent circuit for the switching devices. So first, let's replace switches with equivalent circuit. So do this now, hit the pause button, and when you are ready to resume, press play. Alright, your notes should look like what I've drawn on here. Now, let's take this a little bit further, and I want you to simplify the circuit for DC analysis. That is, take this equivalent circuit, take this circuit that we've sketched, and do whatever you think you need to do to it to make it suitable for DC analysis. And redraw that in your notes below number 2. Hit the pause button and press play when you're ready to resume. So your notes should look like what I've drawn here. What have we done? Well, a capacitor in DC is just an open circuit, so we've removed all the capacitors. An inductor for DC is just a short, so we've made the inductor a short. And what we're left with is a very simple equivalent circuit that we are able to solve to determine the currents and voltages at all locations. So let's go ahead and do that now. We can write a set of equations to solve. First, we can note that the throw voltage is going to be equal to 12 volts minus the voltage across our 5 ohm resistor. Next, we can write an expression for the pole voltage. The pole voltage is going to be 0.25 times our throw voltage, which is going to equal the voltage drop across the load resistor. And we can solve this to say that Vt is equal to 40 IP, which we can then plug back into the first equation. We finally get that IP is approximately 0.29 amps. If we go back to our first equation, we find that our throw voltage is 11.64 volts approximately. And we go to our second equation and we find that our pole voltage is 2.91 volts. So if we call this equation 1 and this equation 2, we combine equation 1 and equation 2 to get this expression, which we use to solve for IP. We then plug IP back into equation 1, and that gives us VT. We then plug that into equation 2, and that gives us our pole voltage. So we've now solved the circuit. We've now used our equivalent circuit to solve what could be a complex circuit. Until now, we had never seen a resistor in series with our source. And we use a very familiar tool to solve this otherwise complicated system for average quantities. Now, I want to point out that we did the proper and mathematically rigorous approach to solving this circuit, but there is kind of a cheating approach that we could take too. We'll say cheating approach, and that is, say that we didn't want to combine equations 1 and 2. Say that the math is too complicated, or we didn't have a calculator with us, or who knows why. This can come up in more complicated circuits than what we've shown here. But what we can do is we can take an iterative approach. And in this case, we say that, well, we can figure that our throw voltage is going to be pretty close to our source voltage. So let's just start by assuming that VT is equal to 12 volts. Let's see what we get for our current and throw voltage, our throw current and pole voltage expressions. Well, our pole voltage is going to be our throw voltage times 0.25, so we end up getting 3 volts. Our pole current is then 3 volts over a 10 ohm resistor, which is 0.3 amps. Our throw voltage, we can now calculate backwards, so we know what IP and VT are. So therefore we can find our throw voltage from expression number 1, or figuring out what the drop is across our resistor here. And if we calculate this, we end up getting 11.625 volts. Okay, well, so we observe that our throw voltage, our new throw voltage, does not exactly match our old throw voltage. Depending on how accurate we need our circuit to be, we could just say that these quantities are close enough and call it a day. But let's say that we want to be a little bit more accurate. So we'll do a second iteration. So this is iteration 1. Now we'll do iteration 2. So now we start by assuming that our throw voltage is our newly calculated value. We can calculate our pole voltage as being 25% of that, which comes out to be 2.91 volts. And we can find our pole current as being the voltage drop over the 10 ohm resistor as being 0.29 amps. And we can find our new throw voltage, which is again using our throw current through our 5 ohm resistor, finding that voltage drop and subtracting from 12 volts, so using equation 1. And if we calculate this, we find that we have 11.64 volts. And this is conceivably plenty close enough to our most recent guess for our throw voltage, so we could just simply call this circuit solved. So this demonstrates a simple way, a cheating way or a hand calculation way to solve the same circuit. Next, I want to emphasize power balance. So power balance is going to come up over and over in this class, and it's important that we internalize this concept. So using this solved circuit, let's consider the power flows at all locations. The power into the circuit, this is the power from our 12 volt source, is going to be equal to our input current times our source voltage. Our source voltage is 12 volts, and our input current is 0.25 times IP. And if we calculate this, we find that we have 873 milliwatts entering our circuit. The losses in our circuit, there's only one lossy component, and that's that 5 ohm resistor, so we can calculate this as the average of our our DC input current, I squared R, our DC input current squared, times our 5 ohm resistor, gives us a total loss number of 27 milliwatts. And we can get our output power as being the power flowing out of our pole, or rather the power delivered to our load. So we could find this either by multiplying Vp times Ip, or we can multiply Ip squared times our 10 ohm resistor. And if we do this, we end up getting 846 milliwatts. So the first thing to notice is that we can confirm that P out plus P loss does indeed equal P in. So indeed, 873 milliwatts plus 27 milliwatts is equal to, 846 milliwatts plus 27 milliwatts indeed equals 873 milliwatts. So that's true. Next, we talk about efficiency. It's represented by the Greek letter eta for some reason. And efficiency is equal to our output power divided by our input power. Gives us an efficiency of approximately 97%. Efficiency should never be greater than 1. If you have efficiency greater than 1, something is certainly wrong. You've invented some kind of better than perpetual motion machine. So that's always a sanity check on your circuit analysis, is to take a look at efficiency. Oftentimes in simple examples for this class, we'll assume an efficiency of 1, but in real life, efficiency is, of course, never 100%. So that concludes this introduction to equivalent circuit modeling of the single-pole double-throw switch. Next, we'll be talking in more detail about completing this model and considering the discontinuous conduction mode case, where our equivalent duty ratio is no longer equal to our active device's duty ratio.